Hello everyone, this is Anil Reddy, Assistant Professor of Mathematics, MLR Institute of Technology, Hyderabad. Today I am going to explain about Newton-Raphson method. So the overview of the topic is how to find root of the equation, derivation of Newton-Raphson method, and graphical representation, and example of Newton-Raphson method. So in the last session we have discussed bisection method, regular false method, and fixed point iteration method. So all these methods based on the intermediate value theorem, that is to find the interval AB and functional values of the endpoints f of A, f of B must be less than 0. So which means both must be in opposite sign. So one is if f of A is less than 0, then f of B is greater than 0, or if f of A is greater than 0 and f of B is less than 0. So both f of A and f of B are opposite signs. So then only root exists between the interval. And a bisection method, so how to find root of the equation? So we take x naught is equal to a plus b by 2. And we generate the x1, x2 and so on. Next, in regular falsy method, we take x1 is equal to a into f of b minus b into f of a divided by f of b minus f of a. And next root we will find x2, x3 and so on. In fixed point iteration method, so we find xn is equal to nth approximation root xn is equal to pi of xn minus 1. So initial approximation we take x naught, that is a plus b by 2, and x1 is equal to pi of x naught, x2 is equal to pi of x1 and so on. Nth iteration xn is equal to pi of xn minus 1. So this is fixed point iteration method. Now today we are going to discuss the Newton-Raphson method. So this is the last method of root finding technique methods in our topic. So this is used to find, this is also one of the root find technique method, and which is used to find approximate root of the equation f of x is equal to 0. So initially we take an initial x value x naught and we generate, so initially we take x naught which belongs to the interval I. So x naught belongs to the interval I, and we generate x1, x2 and so on, xn. So this sequence, how to generate this sequence? So to generate this sequence, we have to derive the Newton-Raphson method. So the derivation of Newton-Raphson method. So let x naught be the estimate root of the equation f of x is equal to 0, and also let h be the small interval. So such that we write h is equal to we write xn plus 1 minus xn. So this is the interval difference. H is equal to xn plus 1 minus xn, or we can take xn plus 1 is equal to h plus xn. So by using Taylor series expansion, we can write this by using Taylor series expansion. So we have f of x plus n, f of x plus xn plus 1 is equal to f of h plus xn. Okay, so by using Taylor series expansion, we can expand this f of h plus xn as f of xn plus h into f dash of xn plus h square by 2 factorial f double dash of xn and so on. Since h is a small interval, since h is small, so we neglect second and higher powers of h, neglecting second and higher powers of h. So that is f of xn plus 1 is equal to, we write f of xn plus h into f dash of xn. Since h is small, so we are neglecting the second and higher order powers of h. So h square, h cube and so on all are equal to 0. Now since xn plus 1 is the root of the equation f of x is equal to 0, then f of xn plus 1 is also equal to 0. Right, so now we substitute this f of xn plus 1 is equal to 0 here. So we get 0 is equal to f of xn plus h into f dash of xn, or we can write this as h is equal to minus of f of xn divided by f dash of xn. Now substitute this h value here, h is equal to xn plus 1 minus xn. So we get xn plus 1 minus xn is equal to minus of f of xn by f dash of xn. So we can write this as xn plus 1 is equal to xn minus f of xn divided by f dash of xn. So this is called Newton-Raphson method formula. Newton-Raphson method, xn plus 1 is equal to xn minus f of xn by f dash of xn. This is the generalized Newton-Raphson method formula. So initial iteration, if we take n is equal to 0, we will get the first approximation root x1 is equal to x0 minus f of x0 by f dash of x0, and the next iteration x2 is equal to x1 minus f of x1 by f dash of x1, and like this we will continue to get the better approximation root of the given equation f of x is equal to 0. So this is the derivation of Newton-Raphson method. Now we will see the geometrical representation of Newton-Raphson method. So let x0 be the approximate root which is close to the exact root alpha of the equation f of x is equal to 0. Now I am taking the graph here. So xy plane, x axis and this is y axis. Now the curve cuts the x axis. So this is the curve y is equal to f of x, which cuts the x axis at this point, and we say this as alpha, and this will be the exact root of the equation f of x is equal to 0. Exact root of f of x is equal to 0. Now we have to choose the initial guess or initial approximation root x0. So this is the x0 on x axis. So the image of x0 will be f of x0, and this point let us take the coordinate a. This is x0 comma f of x0, x0 comma f of x0. Now draw a tangent at this point. Draw a tangent at this point, and this tangent cuts the x-axis at the point x1. Let us take x1. So x1 will be the next approximation root. Now again draw a image of this point x1. So this will be like this, and this will be b, coordinate point b of x1 comma f of x1. Right, again draw a tangent at this point, and this tangent cuts the x-axis at the point x2. Now x2 will be the next approximation root. So again take a image of this point, and this will be the c of x2 comma f of x2. Okay, and again draw a tangent at this point. So this point cuts the x-axis at x3. And now, so like this we will continue this process. So until to get the better approximation route to the alpha. Now this is the graphical representation of Newton-Raphson method, and how to find this equation we'll see. So x naught will be the approximate root which is close to alpha of the equation f of x is equal to 0. Now at the point a x naught comma f of x naught, which cuts the x-axis at x naught. Okay, x is equal to x naught. So the equation of the tangent at x naught at the point A is y minus y1, that is f of x naught, is equal to slope f dash of x naught into x minus x naught. So since the line or the tangent cuts the x-axis at x is equal to x1 when y is equal to 0. So y is equal to 0, substitute here. So minus f of x naught is equal to f dash of x naught, and this x is replacing with x1, so x1 minus x naught. Now we can write this as x1 is equal to x naught minus f of x naught by f dash of x naught. So this is the first approximation root. So similarly we can find the next approximation root x2, x3 and so on, which is nearer to the exact root of the equation f of x is equal to 0. So this is the geometrical representation of Newton-Raphson method. Now we'll see the example on Newton-Raphson method for find a real root of the equation x cube minus 2x minus y is equal to 0 corrected to 4 decimal places by using Newton-Raphson method. So here the interval is point is not given, initial case is not given, so we have to find the interval a and b, and the root lies intermediate value property. So we can find opposite signs f of a and f of b less than 0. Right, so we choose the value, let f of x is equal to x cube minus 2x minus y is equal to 0. Now consider f of 0. So x is equal to 0, I am taking f of 0. So that is 0 minus 5. This is equal to minus 5, which is less than 0. Now take f of 1. So this is equal to 1 cube minus 2 into 1 minus 5. So 1 minus 2 minus 5. So minus 6, which is less than 0. Next to take the next value, f of 2 is equal to 2 cube minus 2 into 2 minus 5. So 8 minus 4 minus 5. So this is also minus 1 less than 0. Next to take f of 3. So this is equal to 3 cube minus 2 into 3 minus 5. So the 27 minus 9, and this is minus 5. So this is also positive value greater than 0. Right, so this is also positive value. Now the root lies between these two values, f of 2 and f of 3, because this is a negative and this is positive. So therefore the root lies between 2 and 3. Now we can also take the root lies between 0, 0 and 3, and we can take 1 and 2, 1 and 3 also, because we observe here. So this interval length is very large, 0 and 3, and 1 and 3 is also large compared to 2 and 3. So here I am going to take the root lies between 2 and 3. Now take the initial guess. Let I am taking the interval, we can take any value which lies between the interval is 2 and 3. So we can take any value between 2 and 3, or we can take 2. Here I am taking x naught is equal to 2, initial approximation. Now we have to find the x naught is equal to 2. Now we have to find what is f of x here. F of x is equal to x cube minus 2x minus 5. So x cube minus 2x minus 5. This is f of x. And now we have to find the its derivative. F dash of x is equal to 3x square minus 2. Now the value of f of x naught. So this is equal to f of 2. So which is equal to, we have already found 2 cube minus 2 into 2 minus 5. So 8 minus 9. So this is minus 1. And next f dash of x naught. F dash of x naught is equal to f dash of 2. So this is, what is that, 3 into 2 square minus 2. So this is 3 into 4 minus 2. So this is 10. Now by using Newton-Raphson method, formula, we write x1 is equal to, generalized formula is xn plus 1 is equal to xn minus f of xn by f dash of xn. So by taking the initial iteration n is equal to 0, so we write x1 is equal to x naught minus f of x naught by f dash of x naught. So what is x naught here? X naught is equal to 2 minus f of x naught value is minus 1. So divided by f dash of x naught. So f dash of x naught value is 10. So this is 2 plus 1 by 10. This is 21 by 10, 2.1. So we got x naught is equal to, x1 is equal to 2.1. Now similarly we can find f of x1. So f of x1 is equal to, we get 2.1. So substitute in the equation. So 2.1 whole cube minus 2 into 2.1 minus 5. So this is equal to 0.061. And next f dash of x1. So this is equal to, what is f dash of x? 3x square minus 2. So substitute here. So 3x square. So 3 into 2.1 whole square minus 2. And we'll get 11.23. Now the next approximation root, x2 is equal to x1 minus f of x1 by f dash of x1. So what is x1 here? 2.1 minus f of x1, 0.061 divided by 11.23. So we get 2.09456. And next approximation root, so similarly we can find x3. So x3 is equal to x2 minus f of x2 by f dash of x2. So substitute x2 value here and find f of x2 and f dash of x2. So we'll get 2.0945. So approximately these two values are same. So we can stop the process. So the required root is x is equal to 2.0945. So which is the required root of the equation f of x is equal to 0. So in today's session we have discussed Newton-Raphson method. And in the next session we will discuss numerical integration. So in numerical integration we will see trapezoidal rule and Simpson's 1/3 rule and Simpson's 3/8 rule.